Black holes, think about it, we just took a huge star that was actually a red supergiant and we folded it down into a space the size of a dot. Actually, it's supposed to be so small it's a mathematical point, which means you couldn't even put a dot there. With me? So we've got a dot that really is smaller than a dot that a supergiant has folded down into. How massive is that? You can't even do the teaspoon thing, right? Now, do you remember what we learned about Einstein's theory of relativity? And he said that space was a fabric and that gravity bends the fabric of space. Remember that? Okay. So remember we looked at this and we saw that the sun or the earth or anything presses down on the fabric of space. You got it. It just clicked. I saw it. So what does a black hole do to the fabric of space? It really, really pushes way down in the fabric. Now, this is looking at it from the side. That's a good question, but as far as I know, I don't know. So I'm sorry. As far as I know, I don't know. So I've never heard of it ripping space. But I'll be honest with you. This whole idea of space being a fabric freaks me out because I've always thought of space as a vacuum, and apparently it's not. And so you have to be able to think in a fifth dimension, which I can't. I'm not a physicist, you know. I have trouble with that. Dylan.
What do we think is in a black hole?
Gravity. And the trick is this. The reason it's called a black hole is if we were to draw this looking down on it, it would look like this. Okay, with this being this part. Anything that gets into this called the event horizon gets sucked in. And that's why it's a black hole. It sucks light in. It sucks stars in. Anything that gets within the event horizon will literally be sucked in and crushed because of the immensity of the gravity. Now, where does this application take us? Well, a lot of scientists believe that that's what holds galaxies together, is black holes. Yes, most astronomers today believe that at the center of galaxies are black holes to hold the galaxy together gravitationally. In next week's class, you're going to actually, I'm going to go through the differences of a black hole and how that works and a white hole and how that works. Because as you go towards, yes, and it is mathematically just as accurate, the reason evolutionists never tell you about white holes is it requires somebody to have started it in the first place. But the math, if you're a physicist, works just as well with white holes as it does with black holes. And I'll explain all that next week. But the trick is this. If you shoot an astronaut towards this event horizon, because of the gravity involved, remember, gravity dilates time. It slows time down. And so as you move towards this, you're going slower and slower and slower. Time is going slower and slower and slower. And then when you cross the event horizon, it's supposed to throw you back in time. And that's why in sci-fi movies, when they have to go back in time, they sling them through black holes, because that's supposed to cause the time to actually reverse and go backwards. Okay, and that's all I'm going to say about that right now, because we have other things to do. But I will talk to you next week about black holes and white holes and the implications and the whole starlight and time issue. How could the creation be 6,000 years old, and yet we see distant galaxies that are thousands of light years away? And there are very good explanations, not that any of them is necessarily right, but there are a lot of good scientific explanations. And part of the reading you're going to do and part of the explanation of next week's class is going to be that the evolutionists, the Big Bang people, have the same problem we do. They have a starlight and time problem too, because they can't explain how the Big Bang occurred as they describe it. And yet, how did the light get to the most distant portions of the universe? They actually have a starlight and time problem just like we do. They never tell you that, though. They always just go, oh, you creationists, you know? So we'll deal with that next week. Okay, so we did this. Let's go on to find distances. So how do we figure out how far stars are away from us? Well, there's two ways that we can do it. Okay? Yeah, you see him? He's going like this. Okay, so the two ways we can do it is the parallax method or the apparent magnitude method. Now, you tell me which one of those is more accurate. The The parallax, good, because it's based on geometry. And which one is used for the more distant stars? The magnitude, the apparent magnitude one is used for distant stars. So the parallax method can only be used on stars that are close by. Close by. From what I remember, it's like less than 100 light years or less away. So we have to establish what a light year is. So turn to page 412, please. A light year is a distance. It's approximately 6 trillion miles. I don't know about you, but my little brain can't get around 6 trillion. My brain can't even get around a million because I've never seen $1 million or a million anything. You know what I'm saying? It's probably seen a million water molecules in the ocean. But you know what I mean, that I've actually been able to count. Yeah, you can't really see it. I'm with you. Or the grains of sand on the beach, but I haven't counted those either, you know. So anyway, so these are, a light year is how far light can travel in a year, 365 days on Earth. And I want you to understand, and this is something I know it's hard, but you got to keep in mind. When we look at all this stuff, we're looking at it from planet Earth, and so we're trying to translate things from planet Earth. And we define things on Earth time. But that may not be accurate for out there time because the gravitational differences in space. Does that make sense? So I don't know about you, but this whole thing has made my brain kind of shift gears and go, and start stripping gears because I think in terms of Earth time. I don't think in terms of out there time. But we really need to if we're going to discuss this, don't we? And people that'll try to attack creationism will try to discuss with you things that we believe, and then they'll kind of beat you with the fact that we tend to use Earth time. We've got to realize God gave us all our information from Earth because that's where we are, but that doesn't mean it's the same out there. Okay? So anyway, so we got to figure out the distances. And some people would like to say, well, they're just not that far away, but they really are. So 1 light year is 6 trillion miles. It's how far light can travel in a year. Remember, it only takes light 1.3 light seconds to get to the moon. That's fast. It only takes light 8.3 minutes to get to from the sun to us, and that's 93 million miles, and that's 8.3 minutes. So a light year is a long way. I just want you to understand 6 trillion miles is a long way. And okay, I'm just seeing, okay, so that's just telling you light years are distances. Now the parallax method, how you do it is this. You find a star and you drop an angle on it at one time, and then 6 months later, when we're at the farthest point in our travels around the planet, then you're going to drop an angle on it the second time. And when you do that, you should get 2 different angles. And that's why you need a star that's fairly close, so within 100 light years. When you do that, you notice that the star seems to shift. And the reason the star seems to shift is because your location has shifted in the universe, hasn't it? So when you use those 2 angles, it's called triangulation, and I think it's how GPSs work. But anyway, I know triangulation is used on Earth to try to fix places where somebody is. And so you use this triangulation and you can calculate how far away that star is. It only works on stars that are fairly close because if you got a star that's far, far away, you're not going to see this shift, are you? It's just too far away and it won't seem to shift. So you need them close enough that you can see that shift. But then you're using geometry to determine how far the star is away, and that's why it's so accurate, because you're actually using triangulation and geometry and angles to figure out what the distance is. Do you have a question?
Find out how distance is away, but you need the distance to figure
No, you don't. You're using the angles. And when you haven't had geometry yet. But when you know those 2 angles, you can figure out the distance. Yeah, it's geometry, which is scary math to me. Calculus doesn't bother me, but geometry freaks me out. So just go figure, right? All right. Now, the other method is called the apparent magnitude method. And that one, you are required to have a Cepheid variable star near the star you're trying to determine the distance on. And the reason is because Henrietta Leavitt, figured out, after studying all sorts of Cepheid variables, she figured out that their pulsation period could be directly correlated to their absolute magnitude. Now you got to grab that or none of the rest of this is going to make sense. Their pulsation period was directly related to the brightness of the star, the real brightness of the star. If it had an extremely long pulsation period, it was a very bright star. If it had a couple day pulsation period, it was a not so bright star. And therefore, she could actually just watch the pulsation period and she could figure out the absolute magnitude, which is cool when you think about it. Now, I kind of wondered why. And here you see the short, this is days, the short pulsation period has a much lower absolute value than the longer pulsation period. Do you see it? And this explained to me why, and this helped me. I hope it helps you. I had to look at this for a while, and then it made sense. When the star is small, okay, obviously not real bright, and then its pulsation period is determined by how big it gets, because then it progressively gets smaller. And so if it's got a long pulsation period, it actually bigger because it took it longer to get smaller again. Does that make sense? Whereas one with a shorter pulsation period, it went and then it went like this. Does that make sense to you guys? I hope so, because when I looked at this picture, I stared at it for a while and then I thought, oh, that's what it's saying. So if the star has a long pulsation period, it gets bigger literally and takes more time to go back to small. So far, so good? Now, because of that, they were able to map the periods of pulsation on these Cepheid variables that they found throughout the universe. And if a star is anywhere in the vicinity of a Cepheid variable, they know the apparent magnitude of the star by looking at it, right? And then they can determine the absolute magnitude of the star from the Cepheid variable. And if you have that information, the distance equals 10 to the, and this is all the exponent. You don't need this, sweetie. You do not need this. The apparent magnitude minus the real magnitude plus 5 divided by 5, if I remember correctly. And you do not have to use that. Yep, it's right there. Now, what I want you to see in this is this. If you know what it looks like, which is easy to determine, right? And if you can determine its absolute magnitude, which they can from the Cepheid variable, from the pulsation period, then they can plug this in, put it in their calculator, and they can come out with the distance. That's how the absolute magnitude works. I don't know about you, but I did not get that out of this textbook. I got so confused when I read this, didn't you? I'm going, huh? Huh? So I don't want you to learn this. I just wanted you to see it. You can see how this works. You can see this part. You can determine this part by the Cepheid variable. You can plug this in, throw it in your calculator, and you come out with a distance. But it's for faraway stars, and it's not as accurate because you have to make some assumptions. Okay? Okay, so let's look on page 413 on your own, 16.9. It says, which distant measuring method is most reliable, parallax method or the apparent magnitude method? Good, the parallax for sure. It's closer, it's based upon geometry, it's definitely the way to go. Okay, the next thing we get into are galaxies. And remember, every star that we can see with the naked eye is within the Milky Way galaxy. That's what we're told. And it used to be thought that every star you could see was in the Milky Way galaxy. But then Hubble, that the Hubble Space Telescope is named for, I think it's Edwin Hubble. Hubble noticed that when he really focused on distant areas in the universe, he saw distant galaxies. And he's the first one that said, oh my goodness, there's all sorts of galaxies. Now you got to remember, a galaxy is a huge ensemble of stars, usually with 100 million stars or more, and it's held together by a strong gravitational force. And all of a sudden, we thought there were hundreds of millions of stars. All of a sudden, there are hundreds of millions of galaxies made up of hundreds of millions of stars. I don't know about you, but that makes my head hurt. And the neat part about it as a Christian is, the God that spoke that all into being, that knows all of them by name, cares about you and me. Can he handle our problems? I think so. I mean, we have a big God, don't we? And I still can't figure out why he cares about us, honestly. Come on, don't you ever question that when you see what people do? And I go, Jesus, you love us, why? Seriously. So anyway, so let's look at galaxies. What kind of galaxy is that? You tell me. Spiral galaxies. They tend to be kind of flat, kind of spread out, but they have arms, don't they? Okay. And this is a picture from NASA, and it is the largest spiral galaxy that's been found so far. It's 5 times larger than the Milky Way. The Milky Way and the Andromeda Galaxy are the largest ones in our particular group of galaxies. Now, I want you to understand something. This is on that movie I was going to show you. Our solar system's really big, right? Remember when we laid it out and we're a ping pong ball and like we had things all the way to the end of the room? Right, yeah, the ping pong ball is the Earth and the 14-foot pickup truck ball is the sun, and we laid it out all the way across the room. I mean, the solar system's big, isn't it? Okay, with that in mind, if you took our entire solar system and shrunk it down to a teacup, the Milky Way galaxy would be bigger than North America, bigger than Canada, Mexico, and the United States combined if our whole solar system is the size of a teacup. Hello, it's huge. And that's just our galaxy. Our galaxy is 100,000 light years wide and 2,000 light years deep. Remember, it's broad but thin. Okay, the spirals are. And so this one's 5 times bigger than ours. So I have trouble with those. This is an elliptical galaxy. Remember, the elliptical galaxy is actually globular. It's not flat at all. And there's a whole movie that we don't have time to deal with, and it's very good if you ever want to see it, called The Privileged Planet. And what they're establishing in that is that if we didn't live in a spiral galaxy where we do in the spiral galaxy, we couldn't study outer space because of all the disruptions there would be due to the light and other things. So if you get a chance to watch The Privileged Planet, I think you will be blessed by it. It's got some really amazing stuff. As a Christian, you sit there and kind of giggle and laugh because they go, how can this be? How can this be? And you're going, I know. His name is Jesus. Do you want to know him? Anyway, okay, so we have the elliptical galaxies. And then we also have lenticular galaxies, which are narrow like a spiral, and broad, but they don't have the arms. And so once again, all of that would make it so we couldn't study outer space. So God actually made it so we could. And then irregular galaxies just have a strange shape to them, and there are a lot of irregular galaxies too. Now, this is what the Milky Way looks like if you're someplace where there's not a lot of light. I mentioned to you it looks like a white swash across the sky, and that's actually what our galaxy looks like. When people show you pictures of the Milky Way, you would actually have to travel something like 1 billion years at light speed to see our galaxy like this. So I want you to understand, we don't have any pictures of the Milky Way from out there, okay? How do we know it's a spiral? From the looking that we've done, we can see the shape of it, okay? So we know we live in a spiral galaxy. These are just pictures of other spiral galaxies. I just want to be very honest and clear about that. And there's the side version, so you can see how thin it is. We live in Orion's arm. The sun is in Orion's arm. And so let me give you a better picture of this. Here the sun is. You see it? It's like at the mall. You are here, right? Okay, so you see the arms. This is Orion's arm. This is you are here, because there's the sun. Okay, so just give you a feel for where we are. And that's another one. Then the galaxies tend to group together into groups, and our group is called the local group, and it's made up of 31 galaxies. So this shows you the galaxies in our local group. This actually shows you photographs of those galaxies in our local group. The 2 largest ones are the Milky Way and Andromeda. So we are one of the 2 larger ones in our local group, which is made up of approximately 30 galaxies. Remember, each of these galaxies has hundreds of millions of stars. I know, it makes my brain hurt. And then, but it's cool. It's cool when you think about how God loves us. And then the groups come together into clusters. And this is a picture of the Virgo Cluster, because that's our home cluster. And it's made up of a whole bunch of galaxies, because it's these 30 and 50 groups, and then they're coming together in these clusters. And then when you move out even further, okay, so that shows you some of the things that make up the Virgo cluster. And as you back out, the clusters all group together, and they make what's called the Great Wall of Galaxies. And this is, if you were looking at it, if you could go for billions of years into outer space at light speed, you might actually see this. I want you to notice that from what they can tell, there are big voids, and then there are areas that have a lot of galaxies in them. It looks to me like lace. Looks like lace. But the point is, that is the Great Wall of Galaxies. So we are believed our galactic address would be planet Earth in our solar system. And then we live in the Milky Way. The Milky Way is part of the local group. The local group is part of the Virgo supercluster. And then those superclusters come together and make the Great Wall of Galaxies.
Smaller every time you go to one.
I know. So that would be our galactic address.
Are the Great Wall of Galaxies part of something too?
Don't know. I can't even imagine how they figured that much out.
Tiny bit.
Serious stuff, I can't imagine. Well, that's what, now I am not telling you to go watch this movie, but that's what at the end of Men in Black, when they make that part about the guys looking and then, you know, the whole solar system is in a marble and then the marble is in, you know, and he goes out and out and out. I think that's what they're trying to say there, okay? But I'm not saying to see that. I'm not going there. Okay, now, one of the things Hubble figured out was that these, what we thought were stars, are actually galaxies. And you can look at this and tell they're galaxies, can't you? You can look at it and tell they're galaxies. That's because of the Hubble telescope. The Hubble Space Telescope is actually outside of the Earth's atmosphere, so that helps by itself. But the other thing is they focus it on specific areas of the sky, and it will stay focused on that area for however long they tell it, 10, 20, 30 days, so that it is able to actually pick up light that is 1/1,000,000th as bright as what our eyes could see. I want you to think about that for a minute, because it focuses on it for so long. And so then we get pictures of things we couldn't see otherwise. And we're told in that video I'm asking you to watch that if you held up a dime in one direction, you would cover over 3,000 galaxies made up of hundreds of millions of stars each. And there's another direction you could hold up a grain of sand and cover thousands of galaxies. Because they're so distant. And these are just two pictures showing you these galaxies. And I don't know about you, but I think this is beautiful. It's just amazing to me, and it's beautiful what these things look like. And we can't even see this because they're God decorated even the parts we can't see. That's what I guess I'm trying to say. And so to me, this is really amazing. Anyway, the last part of your chapter talks about the universe expanding. And there's a couple of reasons why people think the universe is expanding. And the main reason is because of the red shift that we see in light. So let's look at what redshift is. First off, we're told in the reading that the way you tell what redshift is you use a spectrometer. And spectral analysis is where you bring it in with the telescopes, the big telescopes, you know, that take up a whole building, and an observatory. And then you bend the light, and then you look at the spectrum that comes out of it, and that's how they do spectral analysis. If the light normally is here, notice Roy G. Biv is going this way, okay? And it's spectral lines. Let's say from burning the stuff last week, you saw how different ones had different colors. They have actual spectral lines, very specific, like a fingerprint on different elements. This would be the spectral lines for a particular light. When it's red shifted, all these spectral lines, notice, are a little bit in the red direction. If it's blue shifted, notice all these spectral lines are a little shifted in the blue direction. Does everybody see that? So now the question is, what causes the red shift of light? Well, in your reading, I gave you a little extra reading. There were at least 4 possibilities, weren't there, of what might cause the red shift of light. If the stars are moving away from us, that was a possibility, which actually has to do with the Doppler effect. Remember that when sound is moving towards us, it gets higher pitch because the waves are compressed, and when it's moving away from us, it's lower pitch because the waves are stretched out. Well, they're saying that if something in space is moving away from you, then it's stretched out if the Doppler effect applies to light, and therefore it would make it look red shifted. If it's moving towards us, then it would be blue shifted. Does that make sense? And I want to be very clear, the book even points out that this shows you here, so it's coming towards us, it's blue shifted. If it's going nowhere, it's no shift. If it's going away from us, it's red shifted. And the book tells us that the Andromeda galaxy is actually blue shifted, which if this is actually because of the Doppler effect, that means that it's moving towards us, doesn't it? So that's one possibility. The extra reading you did also said that gravitation could be part of it, that the gravity could actually slow the light down, and the tired light thing was down here, but the gravity can actually slow the light down and throw it to the redshift on it. This second order Doppler effect, you read about it, it's talking about when something is moving at a right angle to you, that they see the redshift of light even in the laboratory. So they're saying that maybe some of these stars or galaxies are moving at a right angle to us, and that's what's causing the redshift. And then the last possibility that was mentioned was tire light, that the photons actually can exchange energy with other photons in the process of coming through space, and that would cause the light to appear redshifted because it'd be tired. Do I understand all of that? No. I'm a cell biologist, but I can get kind of a grip, so I just wanted to give you a grip on that too. So on the internet, it gave this for the redshift, and remember, this would be a secular interpretation because it was on the internet, but that the motion of the galaxies relative to other galaxies could cause the redshift. The expansion of space between the objects could cause the redshift because they're moving away from one another, and gravitational forces warp the course of the light. Those are really 3 of the 4 that we just talked about, aren't they? Okay, so with that in mind, he has an experiment in the book, and I'm not going to stand up here and blow up a balloon that I've put marks on, because I found this, so I don't have to. But what we see is that if we put galaxies on our balloon, and then we blew it up, we would notice that all the galaxies move apart as space is blowing up, if that's the case. Now, he told us there's 3 ways that we can look at this, and it really does matter. An evolutionist would say that there is no center to the universe. And the reason they would say there's no center to the universe, this is the anthropic principle, and you're going to be reading about this week in that extra reading I gave you, okay? They'll say there's no special place in the universe because if there is any center or special place in the universe, then that means there's a God, because that means there's someplace special in the universe. Does that make sense? So they have to repulse that because they're not allowed to think about God if you're a secular scientist. It really is that bad. That's the one way. The second way you can interpret this is how I would interpret it, which is when you blow up the balloon, there's a center to the balloon, right? And so that's a second way, but once again, the secular scientists don't want to go there. And I just want to throw this out to you, that at MIT, there's 2 scientists, Massachusetts Institute of Technology, good school, 2 scientists that have already published papers that it seems like the entire universe is circulating around an axis. That would mean there's a center. Let's not go there. Okay, and then the last one is that the redshift of light really isn't telling us what we think it is at all, and we just don't know for sure. And I want to be clear, Hubble said that the farther you get to the exterior portions of the universe, the more redshifted the galaxies will become. And so we're interpreting it that way even though we're not really sure, okay? So I just want you to be clear on that. All right, so let's see. Let's go over to the study guide. I'm on page 421. And I'm going to do this fast because as soon as we're done with this, then we can all disappear. Right? Yes. Okay. Define the following terms. For nuclear fusion, you should have said something about 2 things ramming into each other and making a bigger thing. For nuclear fission, say something about a neutron splitting a bigger thing into some smaller things, right? And there is energy that you get from the mass that's converted. Critical mass is the amount of isotope to sustain a chain reaction. God bless you. Absolute magnitude, all you have to say for that is the real brightness of the star. Apparent magnitude, how bright the star looks from here. Okay, normal people's terms? Because that's really what it means, right? Light year, how far light can travel in a year? Or you could put 6 trillion miles, that'd be good too. And a galaxy is just a bunch of stars, hundreds of millions of stars held together. I like the word ensemble that it used. It's an ensemble. Anyway, it's a bunch of stars held together by a gravitational force in the center. Number 2, from the inside to the outside, name the 4 regions of the sun. What's the interior portion called? Core. What's the next one? Radiative zone. What's the next one? Convection zone. What's the outer part that we see? Photosphere. Good job. Number 3, how does the sun get its power? That is nuclear fusion. Hopefully you at least said fusion, right? Or maybe you wrote H plus H yields HE. That would work too. Okay, and then it says, in which region of the sun does this process occur? In the core, thank you. What part of the sun do we see? Photosphere. Number 5, we have a CF251, and it's hit with a neutron, and it turns into an SN124 and a CD120. Do we have fission or fusion? Fission. I'm telling you on the test, he's going to make a very convoluted question. Remember that when you have fission or fusion occurring, you end up losing mass and it converts into energy. That should help you, okay? And we will grade your test at the beginning of next week's class, just so you know. All right? So make sure you do that, make sure you bring it, and we will go over it. Okay, let's see. Number 6, 2 helium-4 nuclei collide and turn into a beryllium-7 nucleus and 1 neutron. Is this fusion or fission? Fusion, because it's getting bigger. Number 7, for both the nuclear fusion that occurs in the sun and the nuclear fission that occurs in a nuclear power plant, what can we say about the mass of the starting materials compared to the mass of what we end up with? Good. We end up having more mass at the beginning and less mass at the end because we converted it into energy. But make sure, if he's asking about the mass, make sure you say that you end up with less mass. Okay? Good job. All right, and let's see. Number 8. Why is it impossible for a nuclear power plant to have a nuclear explosion? Yes?
It doesn't have significantly more than the critical mass.
Good. They don't keep a bunch more than the critical mass. Thank you. And therefore, they stop that problem from happening, please, Lord. Number 9, why is nuclear fusion considered a better option for energy production than nuclear fission?
It'd be too expensive and like hard to get.
Well, that's why we don't do it. You're absolutely right. But it's considered a better option because there's no radioactive waste products. Okay? But you are absolutely right about what you said, David. Number 10, if nuclear fusion is a better option, why don't we use it? You just answered that question. Okay, so David already said that it costs too much to make it happen. And I guess that's really it. It's not feasible. Okay, let's see. Number 11, we're going to use the HR diagram for this. And so it tells us the magnitude and the spectral level of each of these. And then on the next page, it says which of the stars in number 11 is most likely our sun. So you find the main sequence star, which is B of those, and it would be B. Order the 4 stars in number 11 in terms of increasing size. So that would be D, B, A, and C. Did everybody get that? Yeah. Okay, good. 14, order the 4 stars in 11 in terms of increasing brightness. That would actually be the same. D, B, A, and C. Okay? Number 15, which is the coolest, the star in 11 that's the coolest? That would be A. Number 16, what similarities exist between novas, supernovas, and pulsating variables? First off, what do they all have in common? They're all variable stars. Their magnitude is variable. Thank you. And then that's the similarity.
I was going to say they were not on the HR diagram.
Good. They're not on the HR diagram, but the reason is because they're variable in their magnitude, right? But then it says similarities. Okay, so we did the similarities. They're all variables. It doesn't ask anything else there. Number 17, what is the big difference? There it is, between novas, supernovas, and pulsating variables. That would be their lifetime. Remember, a supernova, you're done. A nova, it's going to blow up faster because it keeps blowing up. And then the pulsating variable will last the longest. So the lifetime would be the answer there. Is that what you guys got? Yeah? Okay. Number 18, what most likely formed the Crab Nebula? Good. Exploding star or a supernova. Very good. Take it either way. Same thing. Number 19, what are the 2 methods for measuring the distance from the Earth to a star? Parallax and the apparent magnitude. Which of the 2 is most accurate? Parallax. Which can be used to measure long distances? Good. The apparent magnitude. Number 20, why are Cepheid variables so important for measuring long distances in the universe? Now, I don't know if you already got the answer to that, but that should be that we can tell how bright it really is from the pulsation period. That's what it is. And then number 21, what are the 4 basic types of galaxies? Spirals, lenticular, elliptical, and irregular. Then number 22, fill in the blank. Stars group together to form galaxies, which group together to form? I got groups. Groups. And then which group together to form? Clusters, which group together to form superclusters. Okay. Number 23, for the first 3 answers you gave in number 22, give the names that apply to those in which our solar system belongs. So our galaxy is the Milky Way, and our group of galaxies is called the local group, and then those groups come together in the Virgo Cluster, so you're supposed to know that. 24, why do most astronomers believe the universe is expanding? You could just say because the redshift of light that we see. And then 25, if the universe is expanding, does the geometry of the expansion matter? Yes, it does matter. If so, why? Because the theories developed are up on assumptions, and it really depends on whether you believe in God or not as to which assumption you're going to take. And the science works both ways. And I have a number 26 here, which means there's something on your test that you need to know. And I said, what is the redshift of light? The redshift of light is light from distant galaxies have a longer wavelength than they would on Earth. Anytime I add a question to the study guide, that means there's something on the test that I didn't think he asked clearly enough. I will do that with you in biology, and I will do that with you in chemistry too. I write them in. So pay attention to that one. Okay? All right, you guys, have a blessed week. See you next week.